In the second part of the regression lecture, we're going to do inference with respect to the slope parameter beta 1. We'll also consider to test whether the beta 1 is 0 or not, and also consider prediction for the mean and the prediction for a future value. Let's start with the inference for the slope parameter beta 1. Recall that beta 1's estimate, the least square estimate beta 1 hat, has a normal distribution, and if we use the beta 1 hat minus beta 1 divided by the standard error, it has a t-distribution with n-2 degrees of freedom. This distribution will be used for us to consider hypothesis test and also confidence interval. For prediction, we already saw this slope parameter, and we also mentioned that the s-axis in the denominator would determine how accurate is the estimate of beta 1. Denominator big would lead to small variance, and the smaller denominator will have big variance. So we would want the denominator to be big. And that denominator, we know it's the variation in the x variable. So you want the big variation in the x variable when you design the study. Okay. So consider confidence interval. We already know that beta 1 hat minus beta 1 over this standard error has t-distribution. T has the symmetric distribution. Therefore, we can consider the lower bound, upper bound cutoff, use the t percentiles such that in the middle, we have 1 minus alpha as the confidence level. This inequality, we can rearrange it just so that we can have the beta 1 alone in the center, and then everything else on the other side that will give us the confidence interval for the beta 1. The manipulation of this inequality to the form for the confidence interval is similar to how we did in the earlier confidence interval section, so I'll skip the detail. In the end, what we get is that the confidence interval is going to be equal to the point estimate beta 1 hat plus minus the critical value from the t-distribution and times the standard error of beta 1 hat. This critical value refers to on the t-distribution such that to the right of this value, we have alpha over 2 as the probability. Okay, that's the confidence interval. Here's an example. Suppose we have the independent variable x is the time to respond to a stimulus, and y is the time to respond to an auditory stimulus. So we have visual and audio stimulus. We would like to see the relationship between x and y. For this simple data set, the quantities like s-x-x, s-x-y are given to the right, and beta 1 hat is simply the ratio of s-x-y over s-x-x. And then the mean square error is also given as of beta 1 hat is here too. S of beta 1 hat, as you know, is sigma squared. It's simply this MSE divided by the the sigma squared over the s of xx. And then we take the square root that give us standard error. Okay. So it's this s 15.1 divided by square root of this 4008 something that give us this 0.21. So that give us the standard error. And then the t critical value, this notation is not really conventional. So I should really write the t critical value as t.025. T.025 for the t critical value. And then we have the beta 1 hat here is 0.86 plus minus the t critical value and then times the standard error that give us the confidence interval. Okay, so just to emphasize that I had a little mistake. The mistake is around here. This part should be 0.025. Okay, this part 0.025. Okay, that's this example for the confidence interval. For hypothesis test regarding the slope parameter, we also use the same distribution. Recall in hypothesis test, we always have the current belief and also what we wanted to find evidence for. In the regression case, the null hypothesis specify that the slope parameter is 0, which basically means that the y and x are unrelated. The mean of y is not related to x. So beta 1 is 0 in the null hypothesis. In the alternative hypothesis, we say that the beta 1 is not 0 such that the y and x has a relationship, linear relationship in there. For testing, we always construct the test statistic, and then under the null hypothesis, we try to see the distribution of the statistic and use it to compute p-value. So for this case, since we're testing for the beta 1, we'll use the beta 1 hat to start. So beta 1 hat minus beta 1 and divided by the standard error, that's an estimate of standard error that gives us the statistic. And that statistic, we will look at its distribution when the null hypothesis is true. In other words, when the null hypothesis is true, we will be able to tell that this probability of observing the statistic as extreme as in the data, whether that one is big or not. And if that probability is big, then that generally says that simply by chance, we could observe that statistic being like that. But if the statistic give us the p-value is not big, in that case, it would mean that when the null hypothesis is true, it's going to be really rare to have that happen. So we would believe that this null hypothesis should be rejected. Once we reject null hypothesis, we believe beta 1 is not 0, and that basically says that this model is useful to describe the mean of y given x. So we sometimes also call this the test of beta 1 being 0 versus not 0 as the model utility test. For testing, so that was for beta 1 equals 0. Instead of 0, we could test the beta 1 equals to any of the parameter value of interest. For example, if you tested this beta 1 equals a given value, for example, slope equals 1. And in that case, when we consider the statistic, we have beta 1 hat minus beta 1 divided by the standard error. And for p-value, if the research hypothesis, alternative hypothesis is beta 1 greater than the given value, then the p-value would be the area to the right of our calculated statistic in the t-distribution with n-2 degrees of freedom. On the other hand, if the beta 1 is less than beta 1 0 in the research hypothesis, and that's what we suspect or we think that we need evidence to prove that, then the extreme is that the statistic values are too small. So in this case, p-value would be the area under the t-distribution with n-2 degrees freedom, but to the left side of the observed calculated statistic t. The last one is if we have two-sided test. For the two-sided test, we just care whether the slope is 0 versus not 0. Is beta 1 0 versus not equal to beta 1 0. For this case, departure from the beta 1 0 on either side, too large or too small, both indicate that beta 1 hat and the beta 1 0 are truly different. So this p-value in this case would be two-tailed, the left tail plus the right tail. So it's the area and the t-distribution on the, let's say if we use the absolute value of the t-statistic, then it's the two-sided. the ones on the right-hand side, and then double it, because the t-distribution is symmetric. So that's the p-value. Here is the example for the stimulus example. If we do conduct a test for beta 1 equals 0, which is not 0, and we use the ratio of beta 1 hat minus 0 divided by the standard error, in this case, we'll try to see whether this ratio is too big or too small. Therefore, p-value is this twice of or greater than the absolute value. P-value, the test statistic in this case is 3.991. So we just consider t-distribution greater than this 3.991, but we need to double it to get us p-value. In this case, the p-value computed is 0.004. We would conclude that the slope parameter is not 0. So we believe the mean of y given x can be explained by this linear relationship. The computation does not have to be done by hand. Instead, it's much convenient if we try to compute it in R. Here are the R code and output. We put x, the observed values for x, give it as a vector, and then also the values of y also as a vector, and then afterward, we use LM command to carry out the model fitting. In the LM command, we have a left-hand side y, and then the tilde, and the right-hand side x. Here, the y tilde x is a formula. The response variable is always on the left side, and all the independent variables are on the right-hand side. But now we have only just one variable. Even though we only put x, it has a default of including the intercept there. And when we want to see the result of the estimate, least square line estimate, we just use this summary command. Summary will give us the output below. In this output, you first see what you called. It's this LM with the formula. And then it gives you the residues, the summary of the residues, 5-number summary. Residues were defined as the yi, observed yi, minus the straight line, this linear fit, beta 0 hat plus beta 1 hat x. The difference of y with that predicted value is the residue. And the next part is the coefficient table. In that table, what you see, there's the intercept, and there's also x there. Intercept, in the column that says estimate, that's just the beta 0. And with the x there, on the column with estimate, that means the beta 1 hat. And in the next column, it gives the standard error. 0.2164, that's the standard error estimate for the slope parameter beta 1 hat. And in the next column are the t values, simply is the ratio of beta 1 hat minus beta 1 divided by the standard error. The beta 1, I'm sorry, in this case is beta 1 hat minus 0 because t value here is testing hypothesis that beta 1 is 0. So it's the model utility test. Then the next column gives the p-value, is the probability of greater than 3.991, and then multiply by 2 because it's two-sided test. Beyond this table, there's also something else below. What's below here? One is talking about the residual standard error. And here is 15.1 on 8 degrees of freedom. That basically says that the 15.1 is the mean square error. Sorry, this is the residual standard error. A mean square error, yes, correct. Is the mean square error, and then it's on the 8 degrees of freedom. And the next one is the multiple R squared. That multiple R squared is an important term. It's used to refer to how much of the variation is explained by the regression line. We want this multiple R squared to be as big as possible. This value is between 0 to 1. If the value is closer to 1, that's great. The dotted line explains the relationship very well. But if this multiple R squared is closer to 0, then the relationship is similar to just the random spread around. So we want this R squared to be close to 1 as much as possible. Another term for this multiple R squared is called the coefficient of variation. So this multiple R squared is also called the coefficient of variation. The last one, this gives a statistic, F statistic. This one is simply the square root of the T statistic. And this is 3.991 squared is the TF statistic. And for that one, the p-value produced should be same as the p-value for this beta 1 hat test. Okay, so that's about this hypothesis testing part. If we wanted to have a confidence interval regarding the slope parameter, how do we do that? Confidence interval. We already explained it's going to be beta 1 hat plus minus the critical value of the t and then times the standard error. But we do not have the computation done directly. Instead, we'll have to do it manually. And how do we manually compute this confidence interval? This is done by picking up the parameters, the values here, like 0.86, that's the beta 1 hat. And then plus minus, here's the standard error, 0.2164. And then we use that number to multiply the critical value from the t distribution. That will give us the confidence interval. In this particular example, if we proceed, I'll try to show that in R to do that. For this example, let me show in R. Like here, we have 0.8636, 0.8636. This is the beta 1 hat. And then we have this plus or minus. I'm going to just temporarily do the plus part. Plus, and the standard error is 0.2164. This is 0.2164. 0.2164, and then multiply the t critical value. T critical value is obtained by QT. And inside of the QT, we need to give the percentage. So for this case, if we want 95% confidence interval, we need to put a 975, and then we need to give the degrees of freedom. Degrees of freedom, here, this 8. Residual standard error, 8 degrees of freedom. That 8 tells us the t distribution's degrees of freedom. So we'll put 8, df equals 8 there. So that's the upper bound for the confidence interval. And lower bound of the confidence interval, you just need to change the plus sign to the minus sign. That will give us the lower part of the confidence interval. So in this case, you see the confidence interval of beta 1 is from 0.36 to 1.36. It's relatively narrow. That means that the beta 1 has been pretty accurately estimated. So that's for using the standard error of the beta 1 hat and this beta 1 hat to give us confidence interval for the beta 1. Okay. This next part is the point estimate of the mean regression line. To estimate this mean of y given x when the beta 0, when the x is the x star. When we try to estimate that, we will need to consider a point estimate of that. Simply just to do the point estimate, we just need to replace the unknown parameter by a point estimate of unknown those parameters. So beta 0 hat plus beta 1 hat x star will be a point estimate of this beta 0 plus beta 1 x star. For this point estimate, if you want to obtain it in R, then what you can do is to calculate, just simply use the beta 0 and beta 1 out of the coefficient table and then multiply the x star value. Okay. The next one, the next one is here, when we try to look at this one, what we want to pay attention is that this is a fixed quantity rather than a random quantity, in the sense that x star is a given value, and beta 0, beta 1 is also fixed quantity. There's nothing random there. So when we try to consider any of the inference regarding the mean, this inference about this one, we would try to consider to use the y minus this estimate and then divided by the standard error, right? We'll get to that afterward. So that's talking about the point estimate. The next thing is about the prediction of a future y. For prediction, future y would include both the mean part, the beta 0 plus beta 1x, and then plus the error part. This error cannot be avoided. It's always part of this future observation y. So if you think about what is y, y really contains the mean part, the y of the mu of y with x given x star, and plus the error part. When we try to do the prediction, we couldn't really get the error. Therefore, when we try to predict, we simply just use the estimate of the mu to predict the y. So even though you want to predict the y, but you're using the mu hat again. The mu hat previously was used to estimate the conditional mean. So both of these two different scenarios, estimate of conditional mean and prediction for the future y, both of them are using the same point estimate, this mu hat, to give us the estimate. Okay, but they have some difference. Difference is when you consider the estimate versus you consider the prediction, if we try to look at their errors, that's different. What do I mean by errors is different? When we try to do the estimation, the error is simply the mu hat, which is what we used, minus the true of the mean. The true mean is the mu of y given x star. That part, this difference gives us the estimation error. On the other hand, when we try to do a prediction, what we wanted, the target is the y, but we used is this y, the mu hat. So the error in this case is y minus mu hat. And this estimation error versus prediction error will lead to the two of them have different variances. So how do we consider the variance of those two? Why do we consider variance? Recall, whenever we want to consider confidence interval, we always need the variance, right? So first, in order to look at the variance, let's write the mu hat here. Mu hat contains the beta 0 hat and beta 1 hat. And the beta 1 hat is a linear combination of the y's. So is the beta 0, because beta 0 is the y average minus beta 1 times the x. So when we put them together, it's still linear combination of the y's. Here, we don't need to involve detail, just understand the basic explanation. When we say it's linear combination of y, as you see, it's the summation of some coefficient times the y. So the d here refers to the whole thing in the square bracket. We do not really have to worry that much about the d. That's because the di are all x. Those are given values. There's nothing random there. Okay, so we call them just coefficient. And the y's are independent. Therefore, if they have normal distribution, then this linear combination has normal distribution. And the mean of that is simply the mean of beta 0, beta 1 hat, which is the beta 0, beta 1. And then we put in there, it will give us the mean of the mu hat. And it's exactly equal to the true regression mean of y given x. And then when we try to look at the variance of this mu hat, linear combination, when we compute the variance, will square the coefficient di. So here you see the square here. And variance of y's, all of them are equal to sigma squared. So in the end, what we get is simply just this sigma squared, and then there's the 1 over n, and then plus this ratio. The ratio denominator is how much variation in the data that we were provided to estimate the slope parameter. In the numerator is how much this new observation x star is deviated from the average center of the x. So as you see, this variance of the mu hat has part of that relates to x, part of that is relating to the sample size 1 over n. This sxx also has n terms. It's a sum of variation in the x. So if n is really large because of n in the summation, sxx is also large, and therefore this second term will converge to 0, close to 0, very small. Similarly, when n is large, 1 over n is also very small. Therefore, you see the prediction, this mu hat will have a variance small if n is large. So that explains if you can manage to use a bigger sample size in your regression analysis, it is to your advantage. So once we have the standard deviation of the mu hat, now we are ready to consider the confidence interval for the mu hat, for the mu. So we use the mu hat minus mu and then divided by the standard error. Standard error, we already know the sigma, that's on the previous slide, sigma squared with this term. But sigma squared is not known, so we'll estimate the sigma squared by the mean square error. That's the part that you saw residual sum of square, residual means standard error part. Okay, so we have the sigma squared being estimated by this sample version, the mean squared error, and we take square root, it will estimate the sigma. And this gives us standard error estimate for the mu hat. And the ratio has a t-distribution with a -2 degrees of freedom. Once we have that, we know the confidence interval for mu is simply this point estimate mu hat plus minus the t critical value times the standard error. Okay. And the mu hat is simply just the linear regression part. And this can be obtained by using the critical value of the qt command. And this part comes from the regression output. So that was for the confidence interval. Next part is the prediction interval. We already mentioned for the prediction interval, the error is y minus mu hat. So because of the y minus mu hat, when we try to consider the distribution, again, we'll write it as linear combinations. But this time, even we do not write it into linear combinations, we can write down the variance here. The variance of the difference here is variance of the first plus variance of the second, because the mu hat of y given x star, that's for the future observation, the future ones, this mu hat comes from past observation, and this y is for future observation. They are independent. So this variance, the sum of the variance, second part we already computed, and first part of the variance y is sigma squared. So altogether, what we get is the sigma squared times 1 plus the actual part. Because of this 1, you see, compared to the previous slide, which is estimation error, this part is extra. And with that extra, it will give us bigger variation in the prediction compared to the estimation. So here is the confidence interval or prediction interval for future observation. We first replace the unknown sigma squared by the estimate, which is the mean square error part. And then inside here, we do not need to change because those are all given values. And then we use the y minus mu hat divided by the standard error estimate follows t distribution again with n minus 2 degrees freedom. From there, we know the prediction interval of y would be simply the mu hat plus minus t critical value and then times this standard error. So again, this part mu hat is same as in the estimation part for the confidence interval, but this part we have s squared. Let's look at this again. Compared to the estimation case, what will happen is that the s squared will not converge to 0. Instead, even if the sample size is large, the mean square s squared is still there. And therefore, we will always have a variance in this prediction. Okay. On the other hand, in the estimation part, we do not have that s squared, the first term, and this second term will converge to 0. So for the estimation, when we look at the confidence interval, it'll get narrower and narrower as the sample size increase. But for the prediction, we always have a term there. Okay, so that's what I just explained. Standard error for the prediction error has the s squared there. In comparing to the confidence interval, the second term will be the only term there in the square root. And this second term goes to 0 as the sample size is large, but with the prediction interval, first term will always stay there. So this prediction interval, it will always be wider than the confidence interval. Let's look at an example. Here we are talking about X is combination depth and Y is the strength for a sample of core samples. We want to see the relationship between Y and X here. After computing, we want the slope parameter, we want the confidence interval for the mean strength when the X is 45. And we also want the 95% prediction interval for a future sample when the X is 45. So both cases, we are looking at X equals 45, but we are looking at one is the mean confidence interval for the mean. The other one is prediction interval for a future Y. This computation is beta 0 hat plus beta 1 hat times 45. That's the point estimate in both cases. And then the standard error part for the mu hat is this is the standard error. If you look at it, is this mean square error part. 2.86 here, mean square error part. And then here's 1 over n, and this is x star 45 minus x bar square, and it's sum squared in x. And that finished the computation for the standard error of mu hat. And then afterward, the confidence interval is simply point estimate plus minus, this is the t critical value. In this case, degrees of freedom for the t would be based on the, let's see, for this example, we have a total of 18 observations, and the degrees of freedom would be 18 minus 2, so it's 16 degrees of freedom. T with 16 degrees of freedom is a confidence interval. You can use the QT 0.975 with the DF equals 16 to get it. So that gives this 2.12. Once you put in a critical value, you get a confidence interval. On the other hand, for the prediction interval, you would have the mu hat plus minus the same critical value, but this time you have s squared in it. And the computation will lead to a wider interval compared to the confidence interval. Okay. For this computation, I mean, this example, if you consider different values of the X and consider confidence interval and prediction interval, the gray area is the computed confidence interval for different x. Say I have x here, this is around 10. For x equals 10, calculate the confidence interval that gives here lower bound, there upper bound. And also compute the prediction interval that gives the lower bound here and upper bound there. And when you move on to the next x value, also compute the confidence interval, which is the gray area, a gray lower bound here, upper bound there. And the prediction interval gives lower bound here, upper bound there. As you keep changing the x and do the confidence interval and prediction interval, you see this gray area, gray band. So that's the entire confidence band for the mean regression line. And this area between the two red dotted line, that's the prediction interval. It's obviously much wider than the prediction interval. Okay, so summary, this mu, the true regression mean, this mu, can be estimated by the beta 0 plus beta 1, beta 0 head plus beta 1 head times the corresponding x value. And when we try to predict for a future observation, we use the same value to predict for that. But the difference is that when you do a prediction for a future observation, then it incurs additional variation, and therefore confidence interval will be wider. The confidence interval for estimation is this mu hat plus minus the t critical value times the standard error. And on the other hand, the prediction interval would be the mu hat plus minus the t critical value, but in the standard error part, there's an extra x squared in the denominator. Because of extra x squared there, prediction interval is always wider than the confidence interval. If the sample size goes to infinity, it's very large, this s part, standard error, will be close to 0. But in the prediction interval, we'll always have s squared. That's not going to disappear. So that's about the simple linear regression. And when we have the data, and we would like to do the prediction, how do I do that? I will illustrate here with this example. I have strings and I also have box type as the two variables. And when I try to consider the linear regression, excuse me, I should perhaps first try to read in the data first. Okay, so here. Okay, I already put the data there in the data set. So first set working directory, and here this part is to read in the data. Once we have data read in, then plot it to check whether the relationship is linear or not. Let me run this set working directory and read in the data. So that's the data. The data contains the x and the y and also the observation number index. So the next part is to run the plot. For the plot here, it shows the pretty clear linear pattern. And then when we try to fit the regression line, we'll directly run with this LM linear model. This LM, once we finish running that, to add the straight line to this regression, to this scatter plot, we just need to do the AB line here, AB line with the model on the fitted from previous line, and run this line. It will add this line. This line is the best regression, the least square estimate of the mean regression. Once we have that, the next thing to do is to check what is the coefficient. For this example, what we want to see is we would like to put a coefficient a table, use the summary command to give us the coefficient table. So call summary, you will see these are the output. In the output, you have the residues and also this analysis, the coefficient table here. And in the coefficient table, you see the intercept, which is the beta 0. So here, 0.0339, that's the beta 0. And this part is beta 1 estimate, beta 1 head. And then if we want the confidence interval for beta 1, we'll have to manually do in this case, 3.08 is the point estimate, and then plus minus the standard error 0.1506, and then times the QT. For the QT, 95% confidence interval, we use 0.975, and then when the DF is 28, because we saw this part gives us 0.28 degrees of freedom. So that's the lower bound of the beta 1's confidence interval. And upper bound would be computed similarly. So for the upper bound part, we just do the plus and run it, that give us the upper bound. So that's the confidence interval for the beta 1. The next part, if you want to do a prediction for this one, let's say, suppose we want to predict for the y when x is equal to, let me see. Suppose we want the prediction of y when x is equal to 0.5. Then what you can do is prediction, okay? Predict, put mod here, and you put list x equals a value with 1.5, so we put it here. Why do I put a list here? Because originally, when we feed the model, we have x there. So if we do not specify what is it, it will not tell what is it. So we run this one, it'll give us predicted value. So this predicted value is the mu hat. For this one, if we want the confidence interval of the mu, you'll have to use this value plus minus the standard error for the mu hat, and then times the t critical value. So basically what will happen is that this value, let me write it down. This is our mu hat. Okay, for this mu hat, we need to do plus or minus the QT, the t critical value, just like in the previous case, 28 degrees of freedom, but we need to multiply the square root of the stuff in the standard error part. And what's in the standard error is this, go up, 1 over n here, 1 over n, and then the x star minus x bar square, and divided by the sxx. Okay, for the computation of sxx, I'll first have to do it over here. Sxx, that's equal to the total variation in the x variable. So sum of the x, I'm going to do DAT's x variable minus the mean of it, x variable, and then square that. So that's each of the x variable minus the mean, and then we take the sum. This is the sum of the squared variation in the x variable. And once we have that, afterward, we need also the x star. X star in this case is 0.5. So x star is equal to 0.5. And we're going to do the x star minus the mean of x. The mean of x, we just have this mean of, mean of the y. X star, mean of x. So x star minus the mean of x, and this whole thing, we need to consider it as the numerator after we square it. And this one, we need to divide by the sxx. That's the ratio. So the ratio here is squared in the numerator, sxx in the denominator. And then we also have the 1 divided by the sample size. Sample size was 30. And this whole thing, we take the square root. That will give us the standard error. So I'm going to write this standard error equals that. And then once I have that, now I'm ready for the confidence interval of mu. CI of mu is simply equal to the two numbers. The lower bound is equal to this predicted value. I'm going to call this predicted value as the mu hat. Okay. It's this mu hat minus the standard error times the t critical value qt of 0.975, and then the df equals to 28. So that's lower bound, and the upper bound is similar, but it's mu hat plus. So once we have these two lines, then we have our confidence interval. So let me run these few lines so that I'll have my confidence interval. Okay, just a second, the mu hat part, and then the next few lines. Let's see, what is the lower bound? It's 0.475, and then the upper bound, if we check it, it's this much, 1.8. Now, what if we wanted the prediction interval? For prediction interval, standard error will change, right? So for prediction interval, we're going to copy that, but we'll have to have this 1 plus that for the, I'm missing the s squared. Excuse me, I'm missing s squared. Sorry, just now the standard error, I have the square root, but I missed the s squared. Where do I get the s squared? S squared is this one, residual standard error. This is a point, S is this 0.308. So 0.308, I'm going to put this 0.308 times that. So that is the standard error calculated based on the mean square error. And then this prediction error will have 1 plus that in the square root. So if I run that, this time it's going to be SE2. And then for the prediction interval, it'll be very similar in terms of computation. The only thing changed now is going to be the SE2. And here is also SE2. And this one is going to be the prediction interval. So I'm going to call it PI low and PI up. I'll put parentheses so that I'll print the value for me. Okay, let me run these 3 lines. That gives me the lower bound SE2. Oh, previously the SE, let me rerun the SE part. SE, and then the confidence interval will also rerun it because previously I had missed the standard error part. So running these 2 lines, that gives the lower bound, upper bound, 0.9 and 1.34. Now for the prediction interval part, the values are 0.4 something and 1.8. So now you see how to compute the confidence interval and the prediction interval. So that's all about this regression prediction part. We finished all the regression. Summarize. In the computation in R, all you need is this LM part, and also the summary part for the coefficient table. And if you need a confidence interval for the mean, you would need to take out the coefficient from the table and multiply this t percentile onto the standard error. If you want to do prediction, you first get the predict for the mu hat, and then afterward compute the standard errors. And for whether you are doing confidence interval or prediction interval for the mean or for the future, why the standard errors are computed slightly differently, simply because there is one extra term there. That's all for the simple linear regression. If we have more of the input variables, you simply add the additional variables to the right-hand side. If you have, for example, two variables, you can write x1 multiply x2. That will include both the main effect and the interaction between the two variables. Okay, that's all about the regression.